All right, so we're ready to start.
Yes.
So hi, I'll make a very short introduction. So hello everyone, and welcome to our electrochemical colloquium. Today we're discussing how electrochemistry can be used for organic synthesis. This interfacing of organic synthesis and electrochemistry is becoming very important these days. And even though there were many books published on this and this field has been developing somewhat for decades, still the fundamental electrode processes are somewhat enigmatic, even for some of the simple reactions. So in this colloquium, I hope we'll be able to raise these important fundamental questions for both this field of organic synthesis and the other fields as well, including electrocatalysis and batteries, where we also have partly electrochemical and chemical reactions at the interfaces with organic molecules. Our today's speaker, Professor Kazuhiro Chiba, is the leading expert in organic electrosynthesis, and he has been working in this field for several decades. Professor Chiba received his PhD in 1992 in Tokyo University of Agriculture and Technology, where he later became a professor, and then in 2017 he became the dean, and in 2020 the president of the university. Kazuhiro, thank you so much for joining us today. It's an amazing opportunity for all of us to be hosting you here. So we're looking forward to your talk, and now the stage is yours.
Yeah, thank you very much for your kind introduction. I'd like to thank Andrew and everyone involved for the opportunity to participate in this colloquium today. The topic of my talk is the application of electrolytic method to organic synthesis. For many researchers working in organic synthesis, the use of electrode electron transfer may not yet be commonplace. I'm one of those who thought so, but it is true that I have been fascinated by electrochemical synthesis for 30 years. Ever since I started working with electrodes, today, I'd like to talk about the basic concept of organic reactions based on electrode electron transfer and some suggestions for the future, focusing on my own research. Before I start, I'd like to talk about the major challenges we face today. Material production is not limited to chemically synthesized macromolecules and general chemical compounds. For example, the production of the food that sustains humanity also depends on solar energy, how it is converted into material production and advanced chemical reactions, and how it is efficiently decomposed depends, in the broadest sense, on how well we can control electron transfer. At a time when the natural world and the global environment are in crisis, the grand vision of how to reduce the impact of human activity and make it more human can be found in the organic electrolytic reactions we carry out in our flasks every day. It is precisely this visionary and important message that we need to deliver in response to the question, what can we do for better Anthropocene, which is now a global concern. With these values as background, I'd like to give an overview of the research we have conducted so far, according to the items shown here. First, I'll give an overview and basic concept of organic reactions using electrodes in this introduction. And then I'll talk about the 4 items shown here. I have tried to include explanations of the basics of as much as possible, so that those who are not familiar with electrochemical reactions using electrodes can easily understand them. If you have any questions, I'll be happy to answer them later. Let's start introduction. As you probably know, electrochemical synthesis reactions involve an extremely large number of conditions. In the past, I have only worked on what is called chemical synthesis, but when I decided to try electrolytic synthesis, I had no idea what to choose and how to try it. For example, electrode materials and voltage. I think this is probably a big barrier for most researchers involved in organic synthesis. From another perspective, however, the possibilities for the future that can be gained by considering electrons as reagent as enormous, and it can be seen as a challenge to find important methods that will open the way to the future. From this perspective, I'd like to explain the characteristics and usefulness of electrolytic synthesis, using as examples that electrolytic synthesis reaction in which I have been involved. First of all, here is an example of a characteristic reaction that can be carried out using the electrolytic method. If the potential between the electrodes is fixed at 1.2 volt, the middle compounds is formed almost quantitatively. After this compound is formed, increasing the potential to 1.4 volt, convert it into the compound on the far right. The potential is controlled by simply turning the knob on the electrolyzer. So this sensation is different from the usual organic synthesis reactions, where the amount and the type of reagent are changed. Looking at this part alone, the reaction method may seem very simple and attractive, but the important point here is the choice of electrolyte solution. This reaction will not take place in solutions containing common electrolytes. It is important to note that a nitromethane solution with a high concentration of lithium perchlorate dissolved in it is used as the electrolyte solution. For this reaction, other conditions are not so important. In general, electrolytic synthesis reactions find optimal conditions from a variety of factors such as electrolytic cell shape, size, electrode material, and current density. This figure shown here is taken from a paper by the Waldvogel group at the University of Mainz, an authority on electrolytic synthesis. It is very clearly illustrated. The undivided cell on the left is the simplest, with the anode and cathode in a single vessel and energized by two conductors producing upwards. The vessel has a double structure with cold and hot water flowing outside the reaction vessel to allow precise temperature control. The small unit protruding from the top right is where the reference electrode is placed and is necessary for more accurate measurement of potential. The figure on the right is a typical split cell. The important point is that the anode and the cathode are placed in separate cell units, and the two units are separated by a membrane that prevents the movement of compounds and electrolyte solutions. This allows the substrate and chemical reaction involved in the electron transfer on the anode and cathode side to be dependent. More interestingly, when electrolyte when electrolytes in an undivided cell without any nucleophile like alkenes, nitromethylation took place efficiently. Since this reaction does not proceed at all in a divided cell, this is an example of synthetic reaction that efficiently utilize electron transfer at both electrodes. In addition, there are different patterns of electron transfer at the electrode surface. In the simplest system, substrates are directly involved in electron transfer at the electrode surface, and intermediates activated by them are involved in subsequent chemical reactions. However, there are cases where substrates do not or cannot directly participate in electron transfer at the electrode. In such cases, an electron mediator or redox mediator is used as an electron carrier to achieve the desired electron transfer and chemical reaction. This figure shows an example of using a molecule with a large hydrophobic tag here, attached to the C-terminus of a model peptide as a substrate to solubilize the peptide molecule. The two thiol group in the molecule are both protected by an acetylaminomethyl group, here abbreviated ACM and shown in red letters. The thiol protected by the ACM base is oxidatively converted to the thiol radical, forming a disulfide bond here. However, the substrate containing this peptide moiety is bulky and rarely discharges directly on the electrode surface. Therefore, an indirect electrode oxidation method using an electron mediator has been introduced. The results shown here are the result of electrolytic reactions in which the substrate introduced above are dissolved in the same solvent mixture, and only the supporting electrolyte is changed. All the supporting electrolytes are generally widely used, and the electrode electron transfer should proceed if the appropriate substrate is used. However, it can be seen that the reaction only proceeds in the following two cases. The point here is that the third and fourth supporting electrolyte both have elements in which the bromine ion functions. In particular, it is important to note that the tetraethyl ammonium fluoride contains bromine as an impurity. It is also important to note that the trace amount of impurities can play an important role in electrolytic reactions. Next is the cyclic voltammetry, or CV, which plays a key role in the analysis of electrochemical reactions. The principle is simple. It is continuous record of the amount and the direction of current and the potential is swept at a constant rate. Here, the black and red lines show the CV in the presence of electrolyte and the trace of bromine ions. In the red line, however, the peptide, which is the substrate, is dissolved in solution in which the electrode is immersed. In both cases, the current caused by the oxidation of the bromine anion, that is, the oxidation wave, rises sharply on the right. However, the red line containing the peptides shown a much larger current flow. This indicates that after the bromine anion is oxidized on the anode surface, it immediately receives an electron from the peptide, returns to the bromine anion, and is immediately oxidized on the anode surface. In other words, the bromine anion mediates the electron transfer from the peptide as catalyst, resulting in a greater amount of current. Also, if you take a look at the lower left corner at 0.2 volt, the black line shows a slight expansion of current in the negative direction, indicating that the bromine cation is being reduced, that is, discharges from the electrode. This indicates the reduction of the bromine cation, but little is observed in the red line. This indicates that the bromine cation immediately takes an electron from the peptide to become a bromine anion. Thus, detailed observation of the CV provide important information for inferring the potential transfer process on the electrode. This scheme is an example of the application of the electrolytic method just described on the synthesis of somatostatin, a kind of peptide hormone. Intramolecular disulfide bonds are formed in direct electrolytic oxidation using electron carriers to achieve total synthesis. The above are some examples of basic methods of controlling various chemical reactions by means of electrode electron transfer inserted in a reaction vessel. The examples shown here are mainly what we have actually done, and in fact, many researchers have proposed extremely diverse methods. In fact, and we expected that more innovative methods based on better perspective will probably be developed one after another in the future. I'll continue with the next topic, bio-inspired electrolytic biphasic system. I was particularly interested in the reaction field of living organisms themselves within the concept of chemical reactions by electron transfer. Living organisms form hydrophilic and hydrophobic biphasic systems with cell membranes and micelles in aqueous electrolyte solutions. I thought that these would be important clues for construction of more efficient electron transfer-driven electrolytic reaction system. Of course, it is important to use different polar organic solvent instead of water for more efficient conversion of different organic compounds. Also, the concept of biphasic system is not just a liquid-liquid system, but also include solid-liquid systems such as the electrodes themselves and electrolyte solutions, and some solid surface placed in electrolyte solutions. And my research began with the creation of more effective chemical reaction system while extracting their functions. In general, the electrolytes used in organic electrolytic reactions are also supporting electrolytes, many of which are soluble in organic solvent. Inorganic salt, such as perchlorate, are sometimes used, but in this case, the solvents are often highly polar or have a high boiling point and are often discharged after the discarded after the reaction. This is a major problem for mass production and complicates the operations that are required to separate the products from the electrolytic solution. Therefore, we have tried to reduce the amount of supporting electrolyte solution needed for electrolytic synthesis by introducing a biphasic system into the electrolytic reaction system. An example of a miscible biphasic solution is shown here. We have found that low polar organic solvent, such as cyclohexene, form biphasic solutions with a variety of polar solvent that become miscible upon temperature change. The lower potential solution, polar solution phase can also be used to dissolve the supporting electrolyte. For example, it is now possible to perform an electrolytic reaction in the miscible state, cool it after the reaction, and remove only the low polarity product from the upper layer. This figure shows an example of the application of the miscible biphasic system to an electrolytic reaction system. The top panel shows the flow of an electrolytic reaction in which the miscible biphasic solution is heated, cooled after the reaction is complete, and separated into the two phases. In most cases, the supporting electrolyte is barely dissolved in upper cyclohexane phase, so the product and the substrate can be recovered from the upper phase, while the lower electrolyte solution phase can be reused. The bottom layer is also a way to provide a highly polar electrolytic reaction substrate S1 and the less polar substrate S2 for electrolytic reactions. Again, a miscible two-phase solution is used as the base, but only the region near the interface is heated so that both the upper and the lower solution are miscible. This selectivity places S1 in an environment for electron transfer, and active species generates there continuously react with S2, storing in the upper layer. The apparatus shown this photo was actually designed so that only the center of a reaction tube is cooled, while the top and the bottom are heated. The center is heated and the top and bottom are cooled. Sorry. Using this reaction apparatus, paramethoxyphenol, which has a relatively high polarity, was dissolved in the lower layer, and styrene in the upper layer. And when the system was electrolyzed and the desired hydrobenzofuran derivatives was successfully obtained with high efficiency. The electrolyte solution used in this study was a lithium perchlorate nitromethane solution, and the upper layer was cyclohexene. In addition, we have developed a flow-type electrolyzer that utilizes the properties of this two-phase solution. Our goal is illustrated in the conceptual diagram of the left. The blue-colored electrolyte solution is fixed in the cell, and the yellow-colored cyclohexane solution that dissolved the substrate is used as a mobile phase in continuously electrolyze the product as a cyclohexane solution. The most important part is the method of continuously separating the cyclohexane phase from the cell after it is in phase solution and electrolytic reactions has taken place. The most effective way to do this was to place a fibrous filter made of PTFE, polytetrafluoroethylene, at the outlet of the cell here. The cyclohexane contained in the filter continuously separate from the mixed electrolyte solution in contact with the filter and leads into the outlet. Through this mechanism, we have succeeded in constructing a system that selectively corrects the cyclohexane solution containing the product after the electrolytic reaction is completed by continuously feeding the cyclohexane solution of the raw material mixture to form a mixed electrolyte solution, which is what we are aiming for. Shown here are the result of the electrolytic reaction performed using this two-phase flow system. Relatively good results are obtained using methanol, acetonitrile, and nitromethane as polar solvent, respectively. Shown here is an example of an electrolytic reaction system consisting of a biphasic solution system of normal hexane and nitromethane. This reaction system involves the coupling of two types of olefins, which will be explained later. A substrate with a methoxyphenyl group is activated on the anode surface, while hexenol reacts nucleophilically. In this case, the nucleophile usually requires an excess of about 20 equivalent when nitromethane is used as a sole solvent. When a biphasic system is configured and only a vicinity of the electrode is immersed in a highly polar nitromethane electrolyte solution, the desired coupling reaction proceeds extremely efficiently. Furthermore, no electrolyte is wasted as a product, and additional substrate supply are simply replaced with an easily removable hexane solution. This is seen as a solution to the problem of electrolytic synthesis, which consumes a large amount of electrolyte. This table shows the effect of using the surface condensed electrodes. As mentioned above in entry 1, 20 equivalent of nucleophile hexenol were used, and the yield is 72%. And in entry 2 and 3, amount of nucleophile reduced to 5 and 2 equivalent respectively. The yield are directly reduced to 17 and 14% respectively. On the other hand, when the surface condensed electrodes are used, the yield is greatly improved. Although the structure of the electrolytic cell shown here is extremely simple, it is an example of how the amount of polar solvent and supporting electrolyte, as well as the reagent required, can be significantly reduced properly controlling the bilayer solution system and the electrode installation method. Next, we will show an example of the application of the biphasic electrolytic system to the synthesis of bioactive natural products. My interest in the synthesis of natural products led me to apply this electrolytic reaction system to the synthesis of a series of bioactive natural products called euglobal, obtained from eucalyptus. Euglobal is thought to be formed in vivo by the intermolecular heterodiol reaction of various terpenes with oxidatively activated heterodiene, grandinol, which has been also obtained from eucalyptus. Shown here is an image of an electrolytic cell with electrode wrapped around by PTFE fiber in high polar electrolyte solution with nitromethane as solvent. The polar phenolic grandinol is selectively activated on the electrode surface by using DDQ as a mediator, and The intermediate was then trapped the hydrophobic alpha pherine ring retained on the surface of the PTFE fiber. This is one of the successful results. Without the PTFE fiber, DDQ oxidatively regenerated on the electrode surface would be trapped by the alpha pherine ring by intermolecular Diels-Alder reaction, so the desired reaction would hardly proceed. Simply by changing the type of monoterpene, it completes the synthesis of 6 Yugo identical with natural absolute configuration. These ones. Next, we examine the effect of perfluorinated emulsion as a reaction field from a new perspective. When perfluorinated emulsions were formed in water, certain Diels-Alder reactions were about 100 times faster than those in water dispersion or in usual organic solvent. When the Diels-Alder reaction of quinone formed by electrochemical oxidation of hydroquinone was attempted in this system, the adduct was obtained in high yield. This is due to the intermediate trapping of the unstable quinone by diene. As a recent result of our research, we have also found that electrolysis in acetonitrile, the selectivity of the product can be significantly changed simply by converting the type of electrode. This difference basically depends on the hydrophobicity of electrode surface. Thus, we have realized a new the importance of a very basic research area, electrode electron transfer, that is, what kind of local activation environment to place in an electrolyte solution system, and moreover, what kind of properties the electrolyte solution system should have. We therefore provide a hint for constructing a new chemical reaction system by taking advantage of characteristic of electrolytic reaction system, in which electron transfer and activation can be controlled only at the surface of the electrode, and by utilizing the functions of liquid-liquid or a solid-liquid interface. Chemical bond formation via Hall catalyst. So far, we have introduced some of the properties of organic synthesis reactions by electrode electron transfer. I have also explained how, by introducing a spatially fixed material called an electrode in homogeneous reaction solution as a starting point of electron transfer, the phase of the solution itself can be configured in various ways to bring out properties that are different from those chemical reactions in general homogeneous system. Next, I'd like to talk about the construction of reaction system, focusing on the effect of the electrolyte solution, which is the most important and fundamental reaction field. The concept of Hall catalysis is subject to this talk. In other words, it is an approach to realize new chemical reactions by controlling the reactivity and the stability of cations and radical cation species generated by electron transfer. As I mentioned, in the electrolytic synthesis of Yugo bars, natural product, nitromethane, was used as a solvent, but it has been confirmed that reaction hardly proceeds in other usual organic solvent. This led us to build up a hypothesis that electrolyte solutions also have a great influence on the properties of electrolytic reactions, and we searched for better supporting electrolyte solutions in terms of reaction acceleration. by using Diels-Alder reaction as an indicator. As a result, as shown here, we found that nitromethane with lithium perchlorate has a remarkable reaction acceleration effect. Furthermore, electron transfer can also be effectively realized with this highly polar electrolyte solution. This was an important discovery that will advance the development of subsequent reactions and characterization of electrolyte solution. Here are some examples of reactions using the lithium perchlorate nitromethane electrolyte solutions. When phenol derivatives were activated at the anode, intermolecular cycle addition with various alkanes were profoundly promoted to give corresponding dihydrobenzofuran. Furthermore, dihydrobenzofuran having a carbonyl group emitted strong fluorescence. Therefore, a highly reactive tri-substituted alkane was bonded to silica gel and dispersed. The modified silica gel surface fluoresced as a result of electrolysis of methoxyphenol with an acetyl group in an electrolytic cell. This is important evidence that the phenoxynium ion generated by the electrolytic reaction leads the silica gel surface and complete the 3+2 cycloaddition reaction. The feature of the fluorescent by forming the dihydrobenzofuran ring was applied, for example, to the synthesis of a unit of non-natural RNA that fluoresces. As shown in this figure, changing the substituent of the phenol derivative, the substrate for electrolytic oxidation, also changes the color tone of the fluorescence. Various benzyl cations produced by oxidation desulfurization gave diverse aliphatic alkane and intermolecular cycloaddition product efficiently in lithium perchlorate nitromethane electrolyte solutions. What is interesting about these examples is that the unactivated hydrocarbons, such as aliphatic alkene, give intermolecular cycloaddition product in high yields. These reactions for this will be explained later, but the key is the common electrolyte chamber solution. A lithium perchlorate nitromethane solution used in both cases. With this background in research, I had a good fortune to working with Kevin, Dr. Moira's lab for about a year, starting in the summer of 1999. I was immersed in chemistry in the wonderful environment of Washington University in St. Louis. I was very happy to have a chance for the research of olefin coupling towards the construction of scopoxylic acid skeleton. The discussion with Kevin and the group members were so productive, and it was also very important experience for me in setting up my new research agenda. One of Kevin's many tasks was intermolecular olefin coupling. As shown in the top panel of this figure, an intramolecular unsaturated bond attacks the radical cation generated by electrochemical oxidation of inner ether moiety. The trimethylcyl group in the allylic position is this one. Yeah. Released as a cation, and intramolecular cyclization is achieved. Finally, by further anodic oxidation, the radical becomes a corresponding cation to react with the solvent methanol to complete the reaction. This reaction was an important stepping stone in the development of my subsequent research. As I have just shown, I was interested in what would happen if a similar reaction were carried out in, say, a lithium perchlorate nitromethane solution. In other words, we were interested in the possibility that alkane, which is not activated, would react as a strong nucleophile in this electrolyte solution, while nitromethane, which is a solvent, unlike methanol, has weak nucleophilicity. So even if an intermolecular carbon-carbon bond is formed by electrolytic oxidation, how would the final reaction be completed? On the other hand, unlike methanol, nitromethane is a weak nucleophilic solvent. After returning to Japan, I attempted to combine substrate similar to the olefin coupling and also electrolyze them in the lithium perchlorate nitromethane. The result was completely unexpected. Cyclobutane ring was formed by an intermolecular 2+2 reaction. This reaction proceeded only when electrolyzed. It is also noteworthy that it does not require one electron per one product molecule. The elucidation of this mechanism was scientifically motivating. The choice of an electrolyte solution, lithium perchlorate nitromethane, is important for this anodic oxidation-initiated 2+2 cycloaddition reaction, as is the combination of olefins. Here is an example of a successful reaction, but the presence of a phenyl ether moiety and inner ether moiety on either of two substrates is prerequisite. The anodic 2+2 cycloadditions were also found to cleave the starting alkane and inner ether, respectively, for further electrolysis of the product. Since the cleavage of associated with anodic electron transfer, the molecule with inner ether moiety, which has a low oxidation potential, has corresponding radical cation. As a result, recombination of the reaction partner occurred in 29% yield. This indicated that the cyclobutane ring was cleaved by electrolysis and reconstituted with a new partner. Also, when we attempt a reaction with a substrate without a phenyl ether moiety, we found again unexpectedly that the olefin metathesis proceeds by the electrolysis. That is, the terminal methylene group of the deuterated heptene is neatly replaced by the other sp2 carbon with a methoxy group. This was ununderstandable from the formation of the cyclobutane radical cation intermediate. Here is a proposed reaction mechanism for each reaction. The formation of the cyclobutane ring requires the presence of a functional group with a low potential, such as a methoxyphenyl group, which can provide an electron transfer cyclobutyl radical cation is formed, as described earlier. In other words, the scheme shown below, the cyclobutane ring is completed by the formation of a aryl cation. The aryl cation should accept electron mainly from the inner ether moiety of the starting material. In other words, since the radical cation proceeds in a chain reaction, the electron transfer does not require a single electron per product molecule. On the other hand, if the substrate does not have a phenyl ether moiety, the cyclobutyl radical cation cannot accept an electron by intermolecular electron transfer. So the cyclobutyl ring is not completed and either returns to the original source material or a new olefin formed with an exchange partner. In other words, olefin metathesis proceeds by this mechanism. Yeah, as shown here. Research on this reaction mechanism was conducted by Yohei, Dr. Okada, and others, as you know. At the same time, the question arose as to why, at least to the best of our knowledge, these series of reactions, in our case, proceed efficiently only in relatively concentrated lithium perchlorate nitromethane electrolyte solutions. One key to this is the concept of radical cation or cation catalyzer whole catalysis. Although many excellent studies are known on this subject, we decided to further explore this concept by developing various reactions using lithium perchlorate nitromethane, as well as analyzing the properties of solutions. Shown here an example of the electrolytic Diels-Alder reaction performed with trans-anethol and diene. Anodic oxidation in a lithium perchlorate nitromethane electrolyte solution produced 80 molecules of cyclobutane per 1 electron transfer under the most efficient conditions. This is an indication that the methoxyphenyl radical cation shown here act as a whole catalysis, and the desired chemical reaction can be achieved with a very small amount of electrode-electron transfer. The type and concentration of the solvent and supporting electrolyte have a very significant effect on the extremely current efficient reaction we have just shown. As far as we have tested, this effect was observed when nitromethane was used as a solvent and lithium perchlorate was dissolved at high concentration. We have already shown several examples of electrolytic reaction in the past, and this again suggests that the lithium perchlorate nitromethane electrolyte solution has the ability to produce this characteristic effect. Now here are the cyclic voltammograms, CV, of the samples with the substrate and products dissolved in electrolytic solution, respectively. The blue lines shown only diene dissolved in the electrolyte solution, and the reticle oxidation current is observed up to 1.5 volt. On the other hand, when styrene derivative shown by the red line is dissolved, the oxidation current is observed from around 0.9 volt, indicate that the discharging is occurred from this substrate. The CV of compound 3, which is the product of Diels-Alder reaction, is indicated by the black line. The oxidation potential of this compound is much higher than that of the substrate, and significant oxidation current is observed at around 1.2 volt. Next, with the CVs as a reference, the result measured with diene and dienophile mixed together are shown in this purple line. The respective concentration are matched to the blue and red lines, but oxidation current are well above them. If we sweep further to 1.5 volt and then sweep in the reducing direction, this direction, to the left, we see that the current flowing at that time is larger than in the outward case. That is, the sweep to the oxidation side. This is because compound threes formed one after another by some catalytic reaction during the sweep of potential, and the amplified oxidation current of compound 3 is observed to be larger. Here is how the catalytic current produces a large amount of product. The corresponding radical cation obtained by oxidizing four methoxy beta methylstyrene with the anode on the left react with diene present in the system in a D-type reaction. The resulting cyclohexane ring is then oxidized to cyclohexane ring. The resulting radical cation, resulting cation within the cyclohexane ring is transferred to adjacent intramolecular methoxyphenyl group. This radical cation takes an electron from the starting 4-methoxy beta methylstyrene to complete the reaction. But at the same time, the 4-methoxy beta methylstyrene does not undergo electrode electron transfer, and the chain D-cell reaction proceeds without electrode electron transfer. This is the principle of obtaining a large amount of product with a single electron transfer. Here, the function of the electrolyte solution that supports the generation and stabilization of radical cation becomes important. In other words, it is suggested that lithium perchlorate nitromethane has the ability to stabilize such radical and cation species. We further explore the new electrolyte solution modeled after similar substrate. We focused on the environment of lithium ions in the electrolyte solutions. When we measure lithium 7-NMR in lithium perchlorate nitromethane electrolyte solutions, the signal was clearly observed in a lower magnetic field compared to when acetonol or methanol was used as a solvent. We hypothesized that this indicates that in lithium perchlorate nitromethane, the lithium cation is less susceptible to coordination by the solvent and is closer to bare state. Therefore, we measured the heat of this solution of lithium perchlorate in various organic solvent and confirmed that almost no heat dissolution was generated for nitromethane. Using these facts as an indicator, we measured NMR of various lithium salts in nitromethane and found that lithium FSI and lithium TFSI showed similar chemical shift, which are also observed for lithium perchlorate in nitromethane. Furthermore, the electrolytic cyclobutane formation reaction also proceeds extremely efficiently. This means that, as expected, the environment of the lithium ion is an important indicator of the involvement of the unique set of functions exhibited by the electrolyte solutions. How is the environment of lithium ion formed based on the relationship between ions in solution? To answer this question, Naoki, Dr. Shida, Yasushi, Dr. Imada, and their colleagues conducted experiments from the new perspective. As you know, lithium perchlorate shows excellent functionality when dissolved in nitromethane, relatively high concentration, 1 molar to 3 molar. As a result, detailed investigation using Raman spectroscopy and CV, it was found that lithium perchlorate builds a network structure in solution at relatively high concentrations. minimizing solvation. As a result, it is inferred that lithium cation and the perchlorate anion maintain a certain distance from each other in a network structure and build a polar environment in solution to support whole catalysis. In brief, when lithium perchlorate is dissolved in nitromethane at high concentrations, a network is formed in which multiple nitro groups surrounded the lithium cation from a remote position. The perchlorate anion also become free, and while the entire solution is highly ionic, they are not strongly coordinated to each other. In this environment, radical cations and cations generated by electrode electron transfer are considered to be stabilized. Lithium bisphorosulfonyl emitter, lithium FSI, and lithium TFSI shown earlier are expected to have similar effects to nitromethane. Thus, it is very interesting that a part of an electrolyte solution, which is essential for the electrolytic reaction, has a work to promote whole catalysis. We are here deeply grateful to Ziggy for hosting Yasushi as an international student for 6 months, and while he was enrolled in the doctoral program, which allows him to build up his research work and have a great experience despite the short time he spent together. The electrolytic reaction system using HFIP as a solvent has been pioneered by Ziggy, Dr. Walter Vogel, and we believe that it has some similarities to lithium perchlorate nitromethane solutions. In our case, the addition of small amount of HFIP, the electrolyte solution may lead to further enhancement of electrolyte functionality. We have also applied the HFIP to the synthesis of pyrophenylsteridones alkaloids, as shown here. In this case, we recently found that both risk acidity of electrolyte solution and oxidation potential gap between the aromatic moieties are key factors for the completion of intermolecular bond formation. We present here example of the total synthesis of a series of natural pyrophenylsteridone alkaloids by optimization of the intermolecular coupling reaction, achieving the synthesis with indoline as a starting material and using electrolytic reaction as a key step in the illustration of an electrolytic cell. The electrolytic reaction was used as a key step. The electrolytic reaction is a key step in the synthesis of indolines, which is difficult to achieve by a conventional method, even within our molecule. Okay, I will now turn to the next topic, electrochemical approach towards the peptide and the nucleoside mimics. Over the past 2 years, a great deal of attention has been focused on the development of vaccine and therapeutics, as you know. Now, what I would like to pick up here is the development of a methanol to synthesize peptide mimics and nucleoside mimics by electrolytic reactions based on proline. Proline often plays an important role in numerous bioactive peptides. This is because it has a rising structure that greatly affects the shape of the peptide molecule and can also be used as a stepping stone for fixing the molecular structure, etc. In addition, for nucleic acid, it can form an important backbone of promising nucleoside derivatives, in which the oxygen in the ring forming the ribose. The ribose is replaced by nitrogen and is thus expected to be developed. A key step in this effort is electrolytic oxidation pyridine, the ring structure of proline, this moiety. The modification of pyridine has long been pioneered using electrolytic reactions. However, because pyridine has a relatively high oxidation potential, the nucleophile is preferentially oxidized and decomposed in the presence of a nucleophile. To overcome this, the iminium cation is electrolytically oxidized at a very low temperature, and the cation is pulled in its original state. Then after all pyridine has been converted to the iminium cation, the current is stopped and the nucleophile is fed into the system for the first time to achieve the desired reaction. This is a revolutionary method in the electrolysis. Revolutionary method in that electrolysis does not occur when the nucleophile is fed, so the desired reaction proceeds cleanly. We also present a new method for proline modification by Moeller et al. This reaction synthesizes a bicyclic diterpene unit from a CBZ protected substrate obtained by introducing a methoxy group at the N-alpha position by electrolysis oxidation in methanol. Moeller attempted to introduce a methoxy group to proline and use it as a stepping stone for intermolecular cyclization. However, the problem here is that if a dipeptide, which phenylalanine is attached in advance, instead of the CBZ group is used as a substrate for the electrolytic reaction, the phenyl group will be oxidized and the desired methoxy group will not be introduced. Therefore, the method used here is to first introduce a methoxy group by electrolysis, replace the methoxy group with a dimethylphenyl group. They protect the CBZ group and the phenylalanine phenylalanilate the dipeptide. The reason why the cyclo group is introduced here is the structure sandwiched between electron-rich heteroatoms such as silicon, carbon, nitrogen bonds can be oxidized at low potential to produce the corresponding cation. By this method, they have succeeded in obtaining the desired intermolecular cyclizing product by reintroducing a methoxy group at the desired N-alpha position by electrolysis. The concept of two reaction mentioned above via iminium cation have both been proposed by Yoshida, Professor Yoshida et al., and are called cation pool and electro-auxiliary, respectively. These series of reaction and the development of reaction system utilizing characteristics of electrolytic reactions are a chemically useful method that utilize a mechanism of electrode-electron transfer. And I have been very interested in this reaction system. In such situation, as shown below, we observed an unexpected phenomenon when we electrolyze the proline derivatives using a lithium perchloride nitromethane electrolyte solution. That is, when a proline derivatives with a pyridine skeleton was oxidized at an electrode at around 0 degrees Celsius without a nucleophile with low oxidation potential. And then the nucleophile was added after the electrolysis was stopped. The product was obtained in which the desired position was substituted. This reaction was effective for many pyridine and proline derivatives, yielding substances with allyl groups introduced at the N-alpha position in yield ranging from 68 to 97%. We show an example of arithmetic application of this reaction system to the synthesis of peptide mimics using a compound in which trimethylbenzene is introduced into Boc proline as a nucleophile. The Boc group of N-Boc proline in which a trimethylphenyl group is introduced into an N-alpha position of the proline can be deprotective and converted into the corresponding secondary amine. The secondary amine moiety of a pyridine ring is then attached to, for example, phenylalanine. And finally, the trimethylphenyl group is replaced by electrolytic oxidation, after which it can be replaced with the desired nucleophile. This sequence of reactions overcome many difficulties. One is that the trimethylphenyl group is not released during deprotection of the Boc group, and it is possible to oxidatively release the trimethylphenyl group when the introduction of an amino acid residue with low oxidation potential, such as phenylalanine, to react with various nucleophiles after completion of electrolysis. This means that the last step is particularly important because it uses the lithium perchlorate nitromethane electrolyte solution, which we have shown many times before. To begin with, what we present here is a DNA or RNA analog that is useful as an antiviral agent. One of them is as a nucleoside. As can be seen from the comparison with adenosine, as a nucleoside have the oxygen atom of the tetrahydrofuran ring is replaced by nitrogen atom. Yeah, replaced here. These are two types of pyridine binding site, CN and CC. CN and CC. And many compounds are known to have remarkable antiviral activities. However, both require a multi-step synthesis method. But if this skeleton can be derived from proline, an amino acid with a pyridine ring, there is a possibility that the desired derivative can be stereoselectively synthesized in a simple manner. In this case, we have succeeded to synthesize various other nucleosides, including CN and CC types, in a short process. That is, it was accomplished by electrolysis in the lithium perchlorate nitromethane, followed by the addition of various nucleobases or nucleophiles. The following is an example of the synthesis of C as a nucleoside. The starting material, dihydroxyproline with a protecting group introduced is subjected to electrolytic oxidation to introduce a hydroxy group, which is then substituted with fluorine. The indoor derivative is still selectively introduced by a Lewis acid catalyzed substitution reaction. The key reaction here is the introduction of a hydroxy group into a pyridine ring by electrode oxidation. We have already introduced the introduction of a methoxy group, but if a hydroxy group can be introduced instead, the substitution can be performed more easily with various nucleophiles under milder conditions. The conditions for direct introduction of a hydroxy group by electrolytic reaction are shown here. By using acetonitrile as a solvent and lithium perchlorate as a supporting electrolyte, and adding a certain amount of water to the electrolysis, we have succeeded in efficiently introducing hydroxy group to a wide variety of prolinol derivatives as shown here. Since hydrous acetonitrile is used as a solvent, the reaction apparatus can be configured very simply. The photo shows a glassy carbon beaker used as an anode in the reaction, with a platinum plate inserted in the center of the vessel. Since the reaction can be carried out in an open system, it has an advantage of being easily scaled up. Okay, let me talk about the last topic, large-scale peptide synthesis using tags. As you know, the mainstream of peptide synthesis is solid phase synthesis. But recently, there has been a growing interest in the production of peptide for pharmaceutical and cosmetic applications. In such cases, it is necessary to consider a production of tens or hundreds of kilograms of peptide at times. So continuous synthesis using liquid phase method is very important. And that is, peptides have been recognized as a candidate for medium molecular medicines, which refers to pharmaceutical compounds. So the molecular weights are roughly in the 1,000 to 5,000 range. This class of medicines has more specificity and fewer side effects than conventional smaller molecular medicines. In 2018, over 60 peptides were approved as drugs in the United States, Europe, and Japan. In addition, over 150 peptides are in active clinical development, and more than 260 have been tested in human clinical trials. The tags referred to here are benzyl alcohol derivatives developed in our laboratory, in which highly hydrophobic alkyl chains are introduced at various substitution positions. Depending on the positions of these alkoxy substituents, the acid resistance, correlation, and fluorescence properties differ. Despite its extremely simple structure, we have succeeded in synthesizing large quantity of peptide obtained by successfully binding amino acid to this tag with very high purity. This method of continual chemical synthesis of middle-sized molecule using hydrophobic tags was attempted to develop both RNA and peptide synthesis. 20 years have passed since we first embarked on this method. Basically, amino acids are bound one after another to the hydrophobic tags, and the product bound to the tag dissolved in the upper layer, while all excess amino acid and condensing agents dissolve in the lower layer. Therefore, by using reaction methods such as heating and phase fusing solution, we have achieved rapid multi-step synthesis without introducing chromatography or recrystallization. For promoting elongation reaction efficiently in a short time. Now, to begin with, here is a strategy for the synthesis of peptide with multiple disulfide bonds in the molecule. For example, in the case of peptide with 4 thiol groups, there are 3 possible combinations, even if the reaction proceeds intramolecularly, as shown here in the final step. For this method, it is needed to selectively dissociate them by electrolytic oxidation in advance, and to selectively and sequentially build the desired SS crosslinks. An example of intramolecular disulfide bond formation by model peptide with 4 intramolecular cysteine residue and hydrophobic tag attached to the C-terminus. The 2 thiol groups on the N-terminus side are each protected by ACM and acetylamino-methyl group, and the 2 thiol groups and the C-terminus side protected by the 2 thiol groups at the C-terminus protected by a treated group, this TRT treated groups. When electrolytic oxidation is performed on these substrates in the presence of bromine ions, an intramolecular reaction proceeds between thiols having an ACM group, followed by the reaction between those having a treated TRT group. As a result, we were able to selectively obtain a bottom compound with 2 pairs of intramolecular disulfide bonds. We choose alpha conotoxin S1 as a natural product to use this reaction model. Conotoxin is a group of neurotoxic peptides isolated from the venom of the marine cone snail, genus since cones. S1 has 2 pairs of intramolecular disulfide bonds. We protected the thiol group of the pair we wanted to bind with ACM and treated groups, respectively, to form peptide chain and subjected to the same electrolytic reaction. A series of reaction schemes are shown here after forming 2 sets of disulfide bonds in an electrolytic reaction. The desired alpha conotoxin S1 was obtained by global deprotection with acid treatment. The liquid phase peptide synthetic method has been applied for further synthesis at 100-gram level. We are already working with a startup founded that has successfully produced high purity, high volume synthesis of various commercial pharmaceutical ingredients, such as those shown here. We have shown several examples of peptide synthesis using our hydrophobic tags. This technique is positioned as a polycarbon method in the recent chemical reviews and is currently regarded as one of the ultimate methods. This method is considered to be one of the very nice methods, and it is an important part of the 3rd generation of liquid phase peptide synthesis. This table taken from Albericio's review gives a history of a major peptide synthesis method that have been published in scientific papers over decades. We published this method shown in yellow 2000, and since then, you can see the papers using this method have been rapidly published. This method, which offered a wide choice of reaction solvent, high volumetric efficiency, and significant reduction in the amount of solvent and reagent used, has a significant impact on actual commercial production. First of all, the number of drugs approved is rapidly increased as it is recognized that peptides can be used as pharmaceutical raw materials for a variety of diseases. At the same time, there is a need for safer and cheaper methods to synthesize peptide in large quantities. I myself founded a university startup 18 years ago based on this technology. Since then, the startup has developed a partnership with national and international companies and is currently working with European pharmaceutical manufacturers to begin the commercial production of several hundred kilograms. I'm very pleased that my proposed synthesis method using hydrophobic tags has developed into commercial production. On the other hand, as you know, peptide synthesis requires a large amount of condensing reagent, and once the condensation is complete, all of the reagent become waste. In addition, the synthesis also requires a vast amount of reagent and solvent, which are disposed of. So it is said that several thousand of to several tens of thousands of times more substances are consumed to produce 1 gram of peptide. Based on the recognition of these issues, we decided to investigate the possibility of linking the condensing agent functions to electrode electron transfer. The considering agent for a mid-bond formation is one that removes H2O from amines and carboxylic acid. Radical cation triphenylphosphine of triphenylphosphine generated by electrolytic reoxidation of triphenylphosphine has a high affinity for oxygen, and thus can be used to activate the carboxyl group of F-MOC amino acid in the system. So the system is expected to form an aimed bond with the N-terminal free peptide attached to the tag, as shown here. By electrolyzing this in a cyclohexane acetonitrile biphasic system, activation occurs in the lower layer, while the peptide attaches the tag and the product that has completed the elongation reaction dissolve in the upper layer. Even as peptides are gaining such a greater deal of attention, the long-standing problem of the large amount of waste product has not been resolved. One contributor to waste generation is the coupling reagent, as I mentioned, that enable efficient peptide bond formation. Generally, peptides are synthesized through the repetitive deprotection of peptide bond formation reaction to form a peptide bond between carboxylic acid and amines. Stoichiometric amount of coupling reagent are required while generate stoichiometric byproduct, leading to accumulation of chemical waste. In this regard, the development of a greener peptide synthesis process is identified as a key for green chemistry. To address this issue, catalytic peptide synthesis has emerged. Since Yamamoto reported the bromic acid catalyzed amide bond formation, Various organoboron catalysts have been developed, some of which have been provided effective oligopeptide synthesis. The mechanism of the reaction has been well studied, which has raised researchers in designing more sophisticated catalysts. In addition, recent studies revealed that several metals act as race acid catalysis. These catalysis form active complex with in situ generated esters and promote peptide bond formation while avoiding epimerization. As I mentioned, we envisioned that the development of the efficient peptide synthesis method using potentially recyclable reagent would pave the way and pave the way to an alternative solution. So we showed here by using triphenylphosphine and electrolytic oxidation, we challenged to synthesize the peptide with that condensing agent. Using this reaction system, all the elongation reaction steps were carried out by the electrolytic method. And finally, the synthesis of Proline, an anti-cancer drug, was achieved. The electrolytic peptide synthesis method has been confirmed to efficiently proceed with a condensation of all amino acid and the product and the byproducts such as triphenylphosphine oxide can be easily separated. It is expected to be applied in the near future as a material production method that significantly reduces the use of energy and materials. In this context, we aim to develop the peptide synthesis method using triphenylphosphine. Okay, this is a summary for the condensing reaction. Okay, this table shows the result of optimized biphasic system with cyclohexane acetyl, and the best effect was observed when tetrabutyl ammonium perchlorate was used as a supporting electrolyte. This means that an efficient reaction system can be constructed in which electrolysis is performed in the lower layer and produce a recovered in the upper layer as initially intended. Okay. One of the further challenges in peptide synthesis is freely designed and efficiently carried out chemical synthesis of cyclic peptide. For example, cyclosporine. In cyclosporine, many of the nitrogen atoms forming the amide bond are methylated. This increases the freedom of the rotation of amide bond and thus makes the conformation of the chain peptide flexible. However, the chemical synthesis amide bond formation to secondary amines must be achieved. And further progress in reaction development is essential. Even in the amino bond formation by the electrolytic method, we reported here the condensation reaction of proline and attachment of another amino acid to a secondary amine, such as proline, were accomplished by difficulties. We are continuing our research to solve this problem. And currently, we have succeeded in improving the reactivity of proline significantly and have also been succeeded in attaching proline to N-methylated phenylalanine in high yield. Detailed condition will be announced soon. Okay, in the process of starting for reaction system, based on the concept of bio-inspired electrolysis, we found a solution system with very specific properties. Lithium powered nitromethane electrolyte solution, which has very unique properties. In other words, the stability of radical cation and cations is remarkably enhanced by special electrolyte solution, and many reaction phenomena that cannot be realized in ordinary chemical reaction system have been found. These paved the way for the efficient synthesis of peptide and nucleoside mimics. We feel that the electrolytic method is in the position to open up a new future for the high volume, high purity, and high efficiency synthesis of peptide and nucleic acid drug materials, which are currently the focus of much attention pharmaceutical raw materials. After more than 30 years of my research in electrochemical reaction and chemical synthesis, I strongly believe that organic electron transfer reactions are still in their infancy compared to the sophisticated systems that living organisms have developed over the course of their long evolutionary history, and I expect to see further advance in this field in the future. The significant increase in the number of researchers participating in this field and its revitalization is truly gratifying. I've also been aware that the community is very strong and that there is a great culture of mutual commitment toward higher goals. I have a high expectation that we will fulfill our responsibilities through chemical reaction on the important issue I have outlined here. Okay, finally, I would like to express my sincere gratitude to all of you who have given me tremendous cooperation as my collaborations. Thank you very much. Thank you for your kind attention. Thank you.
Thank you so much, Kazuhiro. It was an amazing talk. I really liked it. And so I think that I really appreciate that you covered so much about the bio-inspired part of the chemistry, because I think this is something that is developing right now, obviously. But also, I guess it started quite recently, right? In terms of electrochemical synthesis.
Mm-hmm.
Do you agree, or has it been like for at least say a couple of decades? But just
definitely, yeah.
Okay, we're open to questions. So if anybody wants to ask a question, you can raise your hand if you want, and maybe I can start with a few questions. So one is about the role of electrolytes. So you mentioned this quite nicely, but I think what your slides show is that there is a strong effect, right? There is a very strong effect of the electrolyte, both probably the salt and the solvent itself.
Yes.
But my question is, how do you see that the mechanisms? So is it stereochemical mechanism? Is it more of a thermodynamic mechanism when dissolution energy changes substantially? Or so what types of mechanisms? Because I think this comes back to actually a lot of things that we discussed at the colloquium for the electrocatalysis field, where a lot of people study electrolytes effects, and there are a lot of hypotheses, but I'm curious about your opinion about this electrolyte effects from the organic chemistry point of view.
It's a key point and a very important point. I condensed that. I researched it for more than 20 years. But that first time it was just a fortune. So I just found the combination of lithium perchlorate and nitromethane. But pretty highly concentrated lithium perchlorate is required, as I mentioned. It's a point. I couldn't understand the mechanism, but very recently, our student found that the vibration changes depend on the concentration. They measured vibration of a solvent and in the condition of a high concentration of lithium perchlorate, the environment of lithium is immediately changes, and a very ionic structure was formed. And as you can imagine, it's an electrochemistry, mainly electrooxidation. So it forms some kind of radical cation or cation. Anyway, so how to stabilize the stabilization of stabilization mechanism is very, very important for the next step chemical reactions. That was a very important key. For example, so we applied, for example, very normal, usual alkene, CC double bond. It's an inert generally, but if it put into that kind of special electrolyte solution, then it stabilizes cation. So it is, so pi electron is easy to move. In other words, it's the nucleophilicity increases so much, you know.
I see.
So,
yeah.
So the solvent condition was very important here.
It's very interesting. I think this is something also that a lot of people in the field of electrochemistry study aqueous electrolytes. And so not based on organic solvents, and certainly not with very complex molecules with lots of different types of bonds. So I think this is what you're telling us is probably also very important for that part of the community to know that there is a diversity of effects that you can expect. And of course, electrophilicity is one of them. Another question that I have is about the electrode materials. So I know that in the field, electrodes, yes, the material itself. So I know that in the field, a lot of people still somewhat ignore it because the catalysis is happening in the autosphere mode, right? It's not like at the electrode itself. So electrode does play a role sometimes, but since usually you just want to generate a radical or generate an anion or whatever else, the molecule that will go into the solution and react somewhere. So then you don't care so much about the electrode as long as it gives you that reactant. The question that I have is, on the electrode side, how often do you see people working with the heterogeneous electrocatalysis in terms of organic electrosynthesis? So using the actual substrate electronic structure, sort of, so the substrate effect, to tune exactly. You showed a few examples, but just a few. So does it mean that it's very rare?
Yeah. So you mean the electrolyte solution is a very homogeneous, and the electrode is a solid one, generally. So what takes place is that on the interface, at the interface of the solid and the liquid. So it means the surface of electrode. In other words, the condition is changed by the electrode material. So, in my case, so most important one in case of electrode, the hydrophobicity is very, very. It affects the reactions. So, for example, so I showed the difference of platinum and carbon, and the product was completely different. So we try to change the hydrophobicity or hydrophilicity of the surface by modifying the surface. Then the product was completely changed. Yeah. So change the philic to hydrophobic, or hydrophilic, then the complete the product will change. So I think basically it's a very simple. And another example I showed, I wrap the by the PTFE, by the very hydrophobic fiber. It's a Teflon fiber I use. Then we control the surface, for example, to trap the hydrophobic one, not to touch the electrode, just to keep before the electrode. Then we can get the selectivity. Only the hydrophilic compound comes through the Teflon fiber and touch on the electrode. Like that way, it's very biological or like enzymatic condition, I think. So by using the controlling the surface environment, we can control the chemical reaction or selectivity. Yeah, it's a characteristic of electrode process, I think.
Right. Yeah, the reason why I was asking this is for example, if we look at the CO2 reduction reaction, right, we have copper, and say if we try to do something like this on platinum or gold or plastic carbon, our selectivity will be very different and the rates will be different, right? Because I mean, the hydrophilicity is probably more or less similar between metals, but then the selectivity is very different because of the interaction between the adsorbates and the metal. So my question was more about how do you see this kind of outlook on the organic reactions? Is it present in the community, or people usually look at this hydrophilicity?
Yeah, I think that kind of discussion is just beginning. Yeah, so it's a reason why. So about 3 or 4 years ago, so we found the difference of the reaction depend on the carbon and platinum, and it was published in Angebande. Before that, only a few papers are published for inorganic synthesis that are affected by electrode materials. So I think it's just starting. So I hope several researchers got interested in that phenomena and try to clarify the general mechanism.
Great. I think this is very important that we touched upon that. Okay. Maybe a few more questions from my side. So I think you didn't mention it, but I'm curious what you think about it. So there are some papers, or there are some hypotheses that say that you can control the enantiomer selectivity of electrocatalytic reactions on the surface by, for example, applying magnetic field and having a specific configuration of atoms on the surface. So do you know if, like, how far this can be pushed? How, like, are there really examples of this?
How far?
I mean, is it something that can be really achieved in experiments in the field? I haven't seen that many works on this.
Yeah. For example, in which reaction?
I don't have any specific reactions, but I think it's if you have 2 possible enantiomers, right? So
enantiomer.
Right. You have two ways to go eventually, but the molecule is the same, it's just different enantiomers. Electrochemically, can you have a selectivity for one, for example, using magnetic field? Or maybe some other ways?
I see, yeah. I know, yeah. Only the case, so if you introduce a chiral compound on the surface of the electrode, yeah, some selectivity can be obtained. Some researchers tried to get selectivity. Yeah. So it's like that way. Yeah.
All right. We have a question from Stan.
Thank you. Hi, Professor Chiba. Thank you for the interesting talk. I was wondering if mostly you're using electrodes that are basically planar, or do you sometimes use also porous electrodes? And I wonder whether you see some differences between using planar or porous electrodes. For instance, in porous electrodes, you would have limited size of the pores, and that would affect selectivity of your synthesis compared to a planar case.
So you mean the very flat one on the pora and sometimes a fiber. So you are interested in the difference of the shape. If you use a pora or some kind of fiber electrode, so we can get more surface area, and we can get more current. So we can shorten or we can scale up the reactions. So depend on the aim. So sometimes we also use, for example, carbon fiber electrode, etc. But not just you mean so it affects some kind of we can whether we can change the react product or not. So it's very difficult. If I think if the surface if the functional group of the surface is different, sometimes a different product will be obtained. So most important one is chemical condition of surface.
I see. Yeah, because the fiber electrodes you're mentioning, I can imagine those fibers are relatively big, so the pores are probably also big. But then I wonder if you used electrode which was made of more like nanoporous material, like I don't know, runny nickel, for instance, where you really have like pores in the size of the molecules that you're synthesizing. If you could actually control selectivity by controlling the pore size of the electrode itself.
Ah, a good idea. Yeah. Very few research is performed, but it's very good viewpoint. So finally, so we'd like to achieve like enzymatic reactions. So we have a chance to control by the size selection, etc. Yeah, that kind of a bio-inspired reaction system by using electrode is a very promising, very important one, I think.
Thank you very much.
Thank you.
Okay, I have also one question about the slide. The best probably would be slide number 30. It's about, you showed a couple of molecules there on the electrode surface.
Just a moment. Just a moment. One by one.
Maybe you can probably select a specific slide in your
Just a moment. Okay. This one?
Yeah. Oh, yes, this would be a very good one. So my question is about, it's very basic, but I think this is where probably, at least maybe a lot of confusion might come from a non-organic chemists. How do you know? So when you have a molecule, for example, at the bottom, you have the reaction happening, and you have a molecule with a lot of different types of bonds, different types of groups. So you have a OH or methoxy group and the cation group on the left, more close to the left side, or maybe that one, doesn't matter. So the question is, how do you know can you predict which bond will break electrochemically when you run the reaction on the electrode? Or you just run it and then you check it afterwards? There's no way you can predict it easily.
Break? from this one, this is
for
starting
example, for example, but in general, is there any way to say which way the reaction will go on the electrode when you have molecules which have different groups and different potential possibilities for reaction to occur?
Oh, general question.
Yes, it's in general. But this is just a good molecule, I think.
I see one hint is we can measure the oxidation potential of the each compound. For example, we can compare this compound oxidation potential of this compound, oxidation of this compound.
Right.
And this one is lower than this one. So we predict that this will be oxidized. And if one electron moves from this compound, then cation should generate cation. So
right.
like that way. So most stable, most probable cation we expect. Then we expect the next reaction. For example, which portion should give one electron to this compound. Yeah, like that way. So we just expect. Then, for example, we check the structure of the product, and rationally we write the mechanism.
I see. So you can only do it after you finish. So you cannot predict that easily. So because, for example, this molecule, it can go to the surface and it can absorb at the surface differently, right? You have different groups, so it can absorb differently depending on which electrode you use. And then the reaction may happen differently as a result.
Yeah, but in organic chemistry, we generally perform the experience and get the product, and from the structure of the product, we can, and after that, computer chemistry follows. Okay.
Yeah. I think it's pretty clear. In that case, it makes sense. And very last question that I have is very simple, but I'm curious if you what kind of experience you have in your lab about the reference electrodes in organic electrolytes. So you use often silicyl chloride, but that is also in an organic solvent. So do you prepare separate reference electrodes for different types of solvents that you use? Or do you use a special set of bridges that you just separates the contamination?
A reference electrode, you mean?
Yes.
Yeah, and to measure the to control the potential, finely control the potential, the reference is very, very important. But in case of organic synthesis, sometimes the productivity is becomes very important. So we generally control not by electrode potential, but just to measure the current, control the current. It's a very easy way. So generally, we like just control current. It's a very easy to control.
Yeah. So it means that the reference, you in principle, it doesn't matter so much how well it is prepared. So what kind of solvent you use, and in that sense, you just use it as your reference. Essentially, you run it in the galvanostatic region. Okay, I think I understand. Yeah.
Yes.
Okay, thank you so much. I think because we're here, it was an amazing talk, and we are really, really grateful that you were able to come so late in your time zone.
No problem.
I know
thank you.
it's a very it's very important for us. Thank you so much. Thank you for
thank you very much. Yeah.
And have a good night.